सर मैं छोटा सा सिर्फ शॉर्ट में दूंगी तो आपको तुरंत स्टार्ट करना है। सर लाइव हो रहा है। Hello and welcome everyone
Hello.
for the webinar series. Today we have a webinar on solvent loss reduction in batch distillation or evaporation by vacuum controller. For this we have an expert, Mr. Sameer Shah, Chief Executive Officer of UD Technologies. Sir has a vast experience in the field of batch distillation and evaporation. So we welcome you, sir, on behalf of Paril University.
Yeah, thank you.
Sir, welcome you. So, sir, can we start the session?
Yes, yeah.
Yes, sir.
Yeah. Welcome to webinar on solvent loss reduction in batch distillation or evaporation by vacuum controller. UD Technologies apply process engineering in kilo lab, scale up and productions. I just give you some brief introduction. Let me say good evening. UD Technologies are obliged to Parul Institute of Engineering and Technology and Dr. Prabha Modi, Head of Department, for this opportunity to present on the subject. This is all chemical engineering students for their bright future career. Just I introduce about UD Technologies. UD Technologies specializes in designing and manufacturing glass pilot plant and process engineering solution with required customization. We are group of process engineers and different branch engineers. UD Technology is a technology-driven company with high professional standards. The company is headed by process engineer and designers who have 27 years of experience for designing various pilot plants and executing projects like bromine recovery, sulfuric acid dilution, hydrochloric acid concentration, etc. We also offer pilot plants for chemical engineering college laboratory, for mass transfer lab, chemical reaction engineering lab, heat transfer and fluid flow lab. So what will you know from this webinar? See, first that you will learn about the basics of boiling point and vapor pressure, certain batch distillation basic, and why secondary condenser is kept on particular batch distillation, why vacuum is applying in batch distillation, second how solvent loss occurs in batch distillation under vacuum, and what is the solution of to reduce the loss. So this is some practical situation that you will enjoy how it is losses are occurring, and what is the solution, and what is the theory behind that which you have already learned in your syllabus, either diploma students or degree students. So I have kept certain because there may be the diploma students and degree students. So I kept somewhat simpler so that every can understand and can enjoy the webinar. See, now first we should discuss about the boiling point. So boiling point, this is open vessel. So when bubble forms and rise on the particularly vapor pressure when overcome the atmospheric pressure, that particular at that boiling point will come. So what is the definition, exact definition of boiling point? That is, boiling point of solvent is the temperature at which total vapor pressure of solvent equals to the system pressure. So here we say the system is the closed vessel, like reactor, batch reactor. So it is a closed vessel. So there may be the decrease in pressure. It may possible. If it is open vessel, then it will the pressure is will only atmospheric pressure. So I go by one example. For initially we will start with the atmospheric pressure. So you already know that what is atmospheric pressure. Atmospheric pressure at mean sea level is 760 mm of Hg or mercury. So at 100 degrees centigrade, vapor pressure of water, it will reaches to 760 mm of Hg, right? And similarly, if the system pressure is increasing or decreases, boiling point temperature will also differ. For example, at 2.5 bar absolute pressure, boiling point of water increases to 127.4 degrees centigrade. It is from 100 degree at atmospheric pressure, and at 2.5 bar it is 127.4 degrees centigrade. And if we are lowering the pressure, that is around 0.01 bar, the boiling point of water is only 46 degree. So it's there are so many changes from 46 to 127, and if it is a very high pressure, the boiling point will be very high. So we are talking about particularly vacuum control. So I have kept this for only pure solvent. So I have taken the boiling point. So if there is a mixture, there may be bubble point and dew point. Uh, so here we take only pure solvent. So it will be easier to understand the concepts. This is the boiling point apparatus. How it is that if we once fill the solvents, heat it, and once vapor is reaches to around thermometer, this thermometer pot, vapors, when it will reaches to the this point, and it have a very good flow. So at that time you will find the temperature here, temperature, that is the boiling point, and this condenser will condense the vapor in the receiver. So now from the boiling point we will come to again now vapor pressure. So vapor pressure for different solvents at different temperatures are given in chemical engineering handbook by Perry up to 760 mm of Hg. So this data is available in Perry. So now how we you use the particular table that will come down. So we can have boiling points at different vacuum from the same table. If you want to calculate the vapor pressure, you can calculate from the end-to-end constants that you have learned in stoichiometry and thermodynamics. Now we shall focus on the water, which is most commonly available solvent, where it is used for different phenomena, like in the cooling water, cooling tower, in the boiler, and is as a solvent in the reaction. So next table shows that at each temperature there is a vapor pressure. At each temperature there is a vapor pressure. See now, see at 760 mm of Hg, it is the temperature is 99.9 or 100 degrees centigrade. So once we will in the descending order, it is 90, 80, 70, 30, up to 30 I have taken. So at 30 it is only the vapor pressure is 31.7 degrees centigrade, 40 is 55.2, like this. So what this table shows, vapor pressure at 40 degrees centigrade is 55.2 mmHg. So what is, in other words, the boiling point is 55 point, boiling point at 55.2 mmHg absolute is 40 degrees centigrade. So now we will again come to the definition of boiling point. The boiling point definition is that the temperature at which solvent vapor pressure is equal to the system pressure. So when vacuum is around 55.2 mmHg, the water will boil at 40 degrees centigrade. Now, how we will see in the industry, there will be vacuum gauges there. Generally, everywhere it is gauge is there, either pressure gauge or vacuum gauge. So how you will check, how you will convert the gauge vacuum from the absolute pressure. So it is a 760 minus 55.2 is 704.8. So when in vacuum gauge, when vacuum pump starts, and it will reaches around 760, depending on the pumps. If it is a watering pump, it will be around 650 to 660 to 700, And if it is water jet ejector, it will be slightly lower. Steam jet ejector is it triple stage ejector, it will come below that. It is nearby 750 or up to 758, 759. uh, so these are the definition of gauge vacuum. See, generally what happens that in the industry, everybody tells about the and the particular in terms of gauge vacuum. That's why I have shown. So I will again go to the about table. So now what we have discussed, that is the if the system pressure is equal to solvent vapor pressure is equal to the system pressure, it is the temperature is boiling point. So at 31.7 mm of Hg, the boiling point of the water is 30 degree, like this, reverse way. So similarly, you can use the table of Perry, that you will find particular boiling point at particular vacuum. So everywhere the all the tables that gives you the absolute pressure. If you will generally say the term is the absolute pressure is, it starts from 0 at 760 mm of Hg, it is a 760 mm, it is atmospheric pressure or 0 bar, and from again it will increases to 1 bar, 2 bar, 3 bar, that is absolute pressures. So now we'll come for the batch distillation. Distillation is widely used unit operation. It is the method of separation based on boiling point temperature, boiling point difference of different solvents in the solution. Like if there is a acetone water or some ternary mixtures are there, so it will there is a difference between boiling point of acetone and water. So depending on the this boiling point difference, acetone and water can separate out. So larger the temperatures difference between boiling point, easier the separation. So there are two types of distillation based on the operation: continuous operation and batch distillation. Continuous distillation and batch distillation. Continuous distillation has constant feed, constant product. Product means it is a low volatile component, constant residue, and constant reflux ratio. This is a steady state operation. Continuous distillation has advantage of constant purity and better control and smaller footprint of plant. Batch distillation has varied feed, varied product, varied reflux ratio. So feed is changing, product flow rate is changing, reflux ratio is also changing. Product quality is also changes. That so batch distillation is unsteady state operation. So unsteady state operation in particular design is more difficult. So now we'll come why batch distillation is generally carried out in the industry. Batch distillation is carried out after the batch reaction. Batch reaction is widely used in dyes industries, bulk drug industries, and fine chemical industries. Batch reaction, when batch reaction is used, when it is used for long residence time reaction, solvents are employed as a medium for reaction. Means there may be the different solids are there, some liquids are there. So everything is added. First the solvents are added, like water or methanol or methylene chloride, toluene. That is, it is used as a medium. In that reactants are added and the reaction is carried out. So medium used for the complete mixing and the for better reaction rate. So after batch reaction, what happened, that solvent is distilled out or evaporated to recover that solvent and concentrate the final solution. Because after that reaction there are number of steps, like certain extraction are there, then drying is there, neutralization are there. So that because of that it is getting concentrated, and so that same solvent can be used again depending on the process condition. Now we shall have one case to understand vacuum control. This webinar says how you will minimize solvent losses using the vacuum controller. Batch distillation and subsequent condensation of solvent vapors get maximum recovery is very common. This is very common in API, that is active for pharmaceutical ingredients, pharmaceutical intermediate and fine chemical industries. Now we'll come to what is I discussed about the setup of the batch distillation, which will get understood how the process is going on. See, generally it is a setup of batch reactor, fractionating column, reflux line, overhead condenser, that may be primary condenser. Majorly there is a primary condenser. Sometimes secondary condenser is also added, where generally in primary condenser, generally it is a cooling water, and second is that is chilled water or brine. And then there is a receiver. Receiver is for recovered solvent and the vacuum source. Now we'll go to the one GA drawing that will give you better idea. Glass line reactor. There is a one. This is stripping column, and this is enriching column. It is vapor line, and this is a shell side shell into heat exchanger where it solvent vapors get in the on the shell side. There is one small receiver is given to control the reflux ratio. This is a manual reflux ratio control. So from here, depending on the solvent mixture in the glass line reactor, one can increase the reflux ratio or decrease the with the valve. There is a subcooler that that will cool the condensate from the silent heat exchanger. This is the two receivers are there. So here there is a vacuum. Vacuum is applied here. How? See, vapor when when we apply the steam or heating media in the glass line reactor, vapor arises, and it's the path is like that. It will go upward in the stripping column. This is the enriching column. So where is when it will and the reflux will come down, reflux will pours in the top of this column. That because of lower temperature, it will take away the high boiling point solvent vapors down to the reactors, and low volatile solvent will go on the upper side. So product will get pure. So one small batch similar, it is a flow diagram what I have said. It's a batch reactor. From here it goes vapors goes here. There is a fractionating column is there and condenser. One receiver is there. From here reflux is doing, or either the product is gone through this subcooler and to the receiver. Here it is the vacuum is applied at the receiver because the vapor path is such that it will you have to apply vacuum here only. If there is a condensers are there, secondary condenser are there, so then you have to apply vacuum here and equalize the vacuum line with the receiver flask and the secondary condenser. So I just increases the scope of batch distillation. Like there in certain cases there are only reflux and evaporation and condensation of solvent vapors, not distillation. In some cases there is fractional distillation to remove the high boilers. In some cases there are also gases also arising like hydrogen chloride, sulfur dioxide. In some reaction there is ammonia is also evolving. So with them solvent vapor also rises. So in the condenser there are also non-condensables may be also present in the batch distillation. As batch distillation proceeds, feed volume in the reactor decreases. So heat transfer area also decreases. Evaporation rate also decreases. To increase the evaporation rate, vacuum is applied. So this is the reason why vacuum is applying. Due to vacuum, boiling point decreases, which eventually increases the temperature difference between hot fluid and inside reactor. This increases evaporation rates. So or effect. So there is a, so we can see from this equation, area is constant, U is constant. We are increasing LMTD. Or I will take one example. Let's suppose if we are boiling water in the reactor and we are applying 125 degrees steam in the jacket. So what happened? What is the temperature difference? That is only 25 degree. So if we will apply the vacuum to around 92.5 degree, 92.5 mm of Hg. So the boiling point will be the 50 degree centigrade. So the temperature difference will be 125 minus 50, which that is around 75. Earlier it is only 25 degree. So simply you will get that your Q will be increasing. So evaporation rate is also increases. That is Q, you know the equation. That is Q is equal to U LMTD is equal to M lambda. Lambda is the latent heat of vaporization of solvent and M is the mass flow rate. So when you increases the temperature difference, it directly proportional to the evaporation rates. So because of this, vacuum is applied. So how, see, once first the reactor is completely filled up to the top, when vapor is increasing and solvent is recovered in the receiver, so again the volume will eventually it will go lower and lower, and the heat transfer area. What is heat transfer area in a cylindrical reactor? That is pi by 4 sorry, pi dl. It is only pi dl. So as it is length or height is decreasing, your heat transfer area is also decreasing. That time, at that time your evaporation rate will also get decreased. So this is the fundamentals of the why vacuum is applied. Batch distillation can run in several ways, maintaining a constant reflux ratio, giving varied overhead composition. That is, distillation is continued until the still, that is the reactor or distillation achieves the desired composition. Varying the reflux ratio, that is giving constant overhead composition. That is when solvent is getting removed from the reactor, the boiling point will rise because of the high boilers in the feed will increasing. So boiling point will again rise. So similarly, we have to increase the reflux ratio as temperature will get increased. So this is the fundas. The distillation is terminated at a maximum economic reflux ratio when the desired steel composition is achieved. Second is the using the repetitive total reflux. So now we'll come to the secondary condenser. Why secondary condenser is used? Secondary condenser is used for two purposes. One is economy and second is the efficient condensation. So we earlier discussed that generally cooling water is used in the primary condenser, and secondary there will be the either chilled water or brine. So why cooling water? Cooling water is the cheapest coolant as it does not require any refrigerant plant. Cooling tower is used on the principle of contact simultaneous mass and heat transfer with the air. So there is only the cost of only fan is will be there. So no refrigerant. Because of that, the cost of cooling water is very low, and because so to reduce the cost of condensation, cooling water used. So now we come to the point that we have seen different vapor pressure at different temperatures. So at outlet temperature of condenser, there is uncondensed vapor. So at outlet temperature of condenser, there is uncondensed vapor, which is not condensed by cooling water. In secondary condenser, there will be the cooler utility than the cooling water. For example, outlet temperature of water may be 36 to 38 degree. Because of now the overall temperature in our country is higher, so practically supply temperature of cooling water we are getting around 30 degrees centigrade, or even somewhere more also. So the outlet temperature may be around 5 to 8 degrees centigrade, that 5 to 8, 8 centigrade higher. So I have taken 36 to 38 degrees centigrade. Coolant is selected up to the 5 degrees centigrade or minus 20 degrees centigrade. This depends on the solvent to solvent and availability. We shall see the table again to understand the situation again. Vapor pressure at boiling point is 760 mmHg and 40 degrees centigrade. It is a 55 mmHg. This vapor pressure is to be condensed with the chilled water. Outlet temperature of 8 to 10 degrees centigrade. Vapor pressure at 10 degree is less than 10 mmHg. We shall come to again table this. This is a table. So up to 40 degrees centigrade. This is only vapor pressure. So we consider that, see, at the outlet around the 40 degrees centigrade, there is a vapor pressure of 55.2 mmHg, which is substantial. It means that it is not condensed. So at the outlet temperature 40 degrees centigrade, there will be no more condensation rates. To get more condensation, we have to use the secondary condenser, where it will cut off the moisture up to that outlet temperature of the uh, secondary utility. I will show you one Excel sheet. Can you see Excel sheet? Hello.
Yes, sir. Yes, sir.
Can you see the Excel sheet? No.
Yes, sir.
Right.
Yes, sir. Continue.
See, you see the Excel sheet. I have workouts at this. So we have seen that it is at 760 mm of Hg. It is in 100 degree centigrade is there. First, when we'll use the cooling water, it will eventually cut off all the in the condenser. It will cut off the up to 45 degree centigrade all the condensation. So I have calculated the particular vapor pressure at this level. Vapor pressure, it is around 71.5. And if you will use the chilled water, which has around 8 to 10 degree outlet, and I have to consider this a 20 degree. So you can see that what is the how much the percentage condensation is there. With the cooling water in only, it is a 90.59 percentage, and with the chill water, it is 9.5. Total for total condensation, it will be 99.74. Right. So what happened that if we use only primary condenser, there will be the uh, around 10% is losses are there. So other, I will show you the second my Excel sheet. In this, I have taken acetone there. So at acetone, it is a 56. The boiling point of acetone is 56.3 degrees centigrade at atmospheric pressure. When we use the cooling water, it will get condensed up to only 54.37 degree. And in the secondary condenser, I have to give the brine around minus 20, 10 degree. So the outlet temperature is around minus 5 degree. So it will get condensed around 42.39 degrees centigrade percentage. So you can see the difference with the cooling water. It is 54.37% and with the chill water 42.39%, right? So there are difference why the secondary condenser is employed in the batch distillation. So now we will come again to the PowerPoint. So this way we have understood why it is secondary condenser. So similar funda is come under when we employ the vacuum. So here is the solvent charts are there. See boiling point at different absolute pressure or absolute pressure, particular vacuum in mm of Hg. This the water is there. So similar table for the water. See at 100 degrees centigrade it is 759.9. Up to it is a 7 at 20 degrees centigrade there is a 17.4 mm Hg absolute pressure and 742.6 under gauge vacuum. Similar, there are different boiling points given ethanol, methanol, ethyl acid. There are the common solvents which are used. Acetone is there, N-hexane is there, toluene. Toluene has higher boiling point than the water. It is around 110 degrees normal boiling point. And when it is boiling, see at 110, it is higher than the vapor pressure will be lower. And if we talk about the boiling point, so at particular vacuum at 36.7 uh, there will be means 36.7 mmHg, there will be boiling point is 30 degree. So you can understand how you will how you will have to design the secondary condenser, primary condensers, and what are the temperature, how the selection of utility I have also understood. See from all these fundamentals you can you can have to select the utility depending on your solvents and the vapor pressure. You can also calculate what may be the your vapor temperature at secondary condenser on the base of vacuum and the your utility. So there in particular batch plant in API there are also different utilities are also available. Sometimes brine is also available. So these are the fundamentals how you have to use the which utility you have to use. Why secondary condenser is used. So now we'll come to the practical plant situation. Basically, we have to understand the why vacuum, how vacuum control will use the to reduce the solvent loss. So in a pharma API and pharma industry, plant is designed for the multi-product. So in the same setup of the glass line reactor to condenser to receiver, there's a they have to design the multi for the different products. Yeah, they will use the same plant. It, and in particular for the different products, they use the different organic solvents. In this scenario, what utility and vacuum source is fixed. How when you have to design the plant, so you will have to fix the utility and the vacuum source. There are a series of such reactors where batch distillation requires and runs at the same time. Means in single plant there may be the number of batch reactors. there may be the same process or the different process, different products, but when we will design, we cannot have the different vacuum source for different reaction or different utility. So what happened that generally they use the cooling tower. Cooling tower is the general first in the primary condenser, secondary condenser they may use the chilled water, and if requires more, then it will go for the brines minus. So solvents are used such as low boiling point to the high boiling point, methylene chloride to toluene in different reactors. So even at the plant stage, designers does not even know that which new product will come when in the bulk drug plant or API plant. So there are continuous product additions are there. Like suppose in lupin is there and cadila gyrodis is there. So they have their research teams develops new molecules, and even not research persons or the plant persons, they does not know which solvent is suitable. So at the particular plant designer does not know. So what happened that, so vacuum what they will use, I have told you that a cooling tower or chilled water is used. Then majorly vacuum source will be the triple effect steam ejector for very high vacuum. However, different stages can be used for different vacuum on available vacuum. So these are the scenario. So what happened in now reality? So we'll have to see the plants, understand and imagine the plant situation, and see that give you the how solvent loss will happen. To have a real case, we presume the utility of cooling water, which I will take 28 degrees the supply temperature and 33 degrees the return temperature. There's a 5-degree delta T. Chilled water I will take as around 8 degrees centigrade to 11 degrees centigrade with full vacuum around, say we'll guess say 750 mm of Hg. Thumb rule. What is the thumb rule? Is for efficient condensation. It should be that at least 25 to 35 degree higher than coolant outlet temperatures. For example, uh, if we have to condense the water at atmospheric pressure, so it is 100 degrees centigrade. So then cooling water is okay. But if you will go for acetone, it is only 58 degree. Yeah, it can condense up to 30. There will the temperature, outlet temperature will be around 33. The temperature difference is 30 plus 30, it is a 63. It will be somewhat higher. So because of that, then we'll have to use the chill water to cut down the vapor pressure arising at the outlet temperature of cooling tower. So again, so you have to take note that I have used efficient, not 100% condensation. 100% condensation is not possible in practical plants. That I have you have seen the in our tables, because of utility is fixed. Utility outlet temperature is fixed. So then whatever vapor pressure at the final utility outlet, that vapor pressure will goes to the vacuum, which is not condensed. There is no 100% condensation. However, in design, even at primary condenser, we will take the heat duty at 100% condensation. But it is not. It is not in. It is in theory. To design the heat exchanger, it will be okay. But in reality, there will be non-condensables are there. Same what I have shown you in the. I will show you my again that sheet, Excel sheet. Like this. It is with the cooling tower, it is 90.95. There will be 9 overall with this utility, it will come around 99.74, means around 1%. And if we go in the vacuum, I have taken this under vacuum also. So if we'll apply the vacuum under 100 mm Hg, the boiling point will be 51.574. So at up to same, will I have considered this with the cooling tower and the chilled water. So the overall, when we talk about the vacuum, Cooling water only condenses 26.73%, and chilled water it will increase the 58.80%. So overall uh, condensation is only 85.53. So for how you will increase the condensation, so that will come the in the now we will see how vacuum control will help you. So I have told, okay. So this is the practical situation. This will go again the vacuum. I have shown the solvent chart where at different boiling point, different boiling point, what is the vapor pressure, or what is the boiling point at particular vacuum. If we'll see around for the ethanol, it is 44, and it is only 20 degrees centigrade. So when we condense the pure solvent, so we'll have to reach will reach to boiling point, and it will get condensed. So we shall now go take the case of toluene and ethyl acetate at 30 degrees centigrade, which is 20 degree higher than the chilled water outlet. Vacuum is around 725 mmHg. At 30 degree boiling point, vacuum required for toluene and ethyl acetate is different. That is 723.3 and 637.5 mmHg. What data shows that toluene shall condense at this vacuum, but ethyl acetate shall not condense efficiently at 725 mmHg, as the boiling point of ethyl acetate shall between 5 to 8 degrees centigrade, right, at this vacuum. So ethyl acetate escapes from the condenser to the vacuum source. I will show again this in this utility. You can see here, when you vacuum reaches, the boiling point will be very low. We are taking the chilled water outlet, it is 8 to 10 degree. So 8 to 10 degree, your vapor pressure will be very high, around 75, this is around 44.9. So it does not cut down the vacuum. Yeah, so it does not cut down the solvent vapors. So there will be the certain vapors will go into the vacuum pump. In reality also, there are similar situation arising in the practical plant also. Reason behind that, they have full vacuum, and their solvents has will escape in that. So even at nearby vacuum pump exhaust or at the utility, there are always solvent vapor smells are also coming. And when they do the material balances, how much they have recovered, they can find there is a solvent loss are there. Means for example, there will be 100 liter as solvent is used, they may got around 60 to 70% recovery. I have faced certain real like, I face certain reality in our industry, that at one batch distillation setup, distillation of organic solvent occurs at atmospheric pressure. Right. So there is one batch distillation are there, and they are removing the distillation. They are removing organic solvent by distillation, which is occurred at the atmospheric pressure. So, particular at plant level, someone thinks that let me recover the solvent fast by applying the vacuum. So our batch time will be reduced and the production will be more. So what they have done, that they have the quick condensation. They have vacuum. They have applied the vacuum, and surprisingly, they found there is no condensation or very little condensation, and face heavy solvent losses. what happens that after applying the vacuum, boiling point is so much lowered and reaches near the outlet temperature of the coolant. So it means that condenser is not condenser, but it act as a heater because the, because outlet temperature is somewhat more. So when vapor goes to the condenser tube, so it will not get condensed. See, again, I have earlier told that the temperature should be around 30 degree lower than the boiling point. So it just passes. And surprising, I have seen this phenomena, and I have told that there is a you have changed. Have you changed the process condition? Have you applied the vacuum? Yes. I have told you keep the again atmospheric pressure. They have changed to again atmospheric pressure, and against the same phenomenon, then they are getting the good condensation. So this is the real example which I have faced in the industry. So I just explained we have discussed in the drawing that we are using cell side condensation. So what happen again that when solvents condense on the cell side of the shell and tube heat exchanger, the exit temperature of the condensed solvent is nearby the boiling point. By that I will show you in the drawing. Yeah, this is cell side condensation. What happens that when the vapor or condenses, it will that in horizontal condenser there will be a dropwise condensation. So what happens then when vapor reaches to the tube's outer on the tube outer surface, it will get condensed and it will immediately drops that, and it will condensate will pass to this level, and solvent vapor will uncondensed solvent vapor will travels to up to the end of the condenser. So what happened that because of dropwise condensation there will be no subcooling of vapor and no minimum uh, subcooling of the condensate. So the outlet temperature of the vapor will be much higher, right? So what happened in this way? We have understand what is the outlet temperature. Uh, 1 minute. So outlet temperature of the vapor or condensate will be higher side. So what happened that in that condenser at the horizontal condenser, though the heat transfer coefficient is very good, but the solvent condensation is lower, solvent recovery is lower. So because even in that we have to use the subcooler with the lower temperature, right? So why subcooler is employed here? See, it is the exit temperature is nearby boiling point. See, as we will give the vacuum, it will again the vapor will boil again because it will come in the under the vacuum. So we have to subcool to certain temperature so that vaporization can be eliminated. In chemical industry, there will be always one pressure, constant pressure from management to reduce the raw material cost. In such cases, solvent losses increase the raw material cost. So now what is the solution? How will think the green? How will think green? Because solvent losses goes to the atmosphere, which is not only the economic loss, but it is a environmental loss also. So direct organic solvent reaches to the atmosphere. So how we will minimize the solvent loss and stop money loss and reduce solvent inventory. If solvent loss is higher, we have to increase the solvent inventory. Eventually, it is hazardous. So there will be the risk factor also to have more inventory. Uh, How efficient condensation can be set by on the multi-product plant. One solution is more cooled coolant shall be used considering the boiling point at available vacuum, which increases the fixed capital cost and working capital cost. And many time it is not possible to use this solution in existing plant. See, whatever plant is designed and by the project department and given by the they cannot add more in the present plant because of the cost, because of the space limitation. So this solution is not possible practically. The proper solution of efficient condensation is to apply appropriate vacuum so that cooling water has maximum condensation and chilled water get shall cut down other vapor pressure. More precisely, vacuum is to be selected such that boiling point shall be 25 to 30 degree higher than outlet temperature. So we'll again go to the solvent chart. See, we have ethyl acetate is there, right? So at the temperature is around 77.2 is the highest temperature. So when we'll use the vacuum, higher vacuum, not 750 mm, sorry, not around this level, 44 or 25.3. So if we'll use the higher vacuum, higher absolute pressure, so what happened that it the boiling point of the solvent will increase. See the again if you see around the 750 725, it will be around zero, right? It will increase the absolute pressure or decrease the vacuum. So your get boiling point will increase. So the cooling tower, cooling water and chill water will condense the ethyl acetate more efficiently, right? So this is the funda of the vacuum control. So if you will use the higher vacuum, or sorry, higher absolute pressure, or then the condensation will be better, right? So this is the photograph of our digital vacuum control panel. It is for the small laboratory reactor or evaporator, where just you have to apply the only to you have to apply you have to keep between the vacuum source, vacuum pump and the reactor, and you have to set the vacuum here in the vacuum controller. It will control the vacuum, give control. It will control the vacuum depending on the set point and give you the control vacuum to the reactor, which will have a better condensation. So now we'll now discuss about the vacuum controller. The vacuum controller are used for between the vacuum source and receiver, so that required vacuum can be applied to the batch distillation or continuous evaporation. So as we have discussed, we have to apply some higher absolute pressure. So as because of it is a triple effect ejector is there, so there is a full vacuum is there. Means full means around 5 to 10 or 2 to 5 torr are there. So not every solvent has needs this reactor. So what we have to do that we have to control the vacuum. So how we will control the vacuum? So for that, vacuum controllers to be placed between the vacuum source and the receiver, or particularly batch reactor setup. As I have told earlier, that we have to apply the vacuum source at the receiver. So we'll have to apply the control vacuum at the receiver. so that cooling water and chill water will efficiently condenses the solvent vapors. So in there is one other case is also there. In batch station, there is a case where the product used to be distilled has higher boiling point, and in mixture there is a low boiling point solvent. So how we can see again I will tell you the system how. See, there are a batch reactor, so there are a multiple solvents are used in the reactor. So how one can separate? So at lower boil there is a mixture of lower boiling point and higher boiling point solvents. So initially you have to take out the low boiling solvent, and then after that you have to remove the higher boiling solvent. So different appropriate vacuum should apply to uh, remove both the solvents. So you need the different vacuum for the this type of situation. However, some batch distillation can be converted into the continuous distillation. So what are the options now? What are the options available for the vacuum controllers? Automatic or semi-automatic vacuum controller is available, which is to be used between the vacuum source and the system. Solvent losses in the batch distillation cell provide a controlled vacuum to system to get the efficient condensation in result in better recovery. Vacuum controller can be customized according to the process steps and process requirement. Like process steps, there will be some boiling point difference is there. The lower boilers are low boil solvents are there. There are certain process requirements are there. So vacuum controller, it is basically now it comes to the either instrument. So that instrument can be customized. See, we have talked about the batch distillation. Batch distillation is quite because of unsteady state operation. So vacuum control is also useful for continuous distillation because there is a constant vacuum requires constant vacuum is there. So it is also useful in continuous distillation. So how we will select the material of construction? It depends on the process requirement. Some have certain gases, acidic gases are there. So depending on that vacuum controller, that is wetted part is to be chosen accordingly. So there are different methods of vacuum control. One is the valve control. There will be on-off control or control valve is employed to cut off vacuum or control the air purge. Means, for example, you have to apply for a lower vacuum like 500 mmHg. So what happen? One on-off valve will cut off when 500 mmHg is coming and open when it will the vacuum absolute pressure will get increased. Or in second way, there is a control valve is also there, so it will purge the air inside such that the vacuum is going to control. When there is a lower need of air, it will purge the lower airflow rate. So, what is vacuum? Now, I will come to the instrument philosophy. So, how any control will that? So, you need have to one is the sensor, one second is controller, and the third part is which is to be controlled. How sense like for example, for if we are talking about the temperature control. So if there is a electrical heating is there, so temperature is heated by the electrical heating. So what you need in the temperature control circuit? One is the sensor, that is temperature sensor. Second is the temperature controller, and third is the heater. Heater means how you will control it. So to give the power to the heater, current to the heater. So depending on the temperature, you will control the temperature by controlling the power supply to the heater. So in this, it is a combination of vacuum transmitter control and electromagnetic valve, that is with the on-off valve with complete panel and inside pipe work for vacuum. Valve sort of when set up vacuum edges and open when vacuum reduces due to the vapor pressure in the system to side vacuum. So this is the valve control. Second idea is the vacuum control to variable frequency track. That is how it controls the vacuum control. VFD shall control the RPM of motor of vacuum pump. Like this. See, this is the vacuum pump. This is a vacuum pump. It is the motor is there. Then VFD will control the RPM of the motor, and eventually it will produce the capacity will be changed of the vacuum pump. So there will be the change in the vacuum level also. It is how it will RPM 1 upon RPM 2 is equal to HP1 upon HP2 square. So these are the relations, equations are there. So how it is that vacuum control and automation can be manufactured as per process application and capacity. See, if you want to have some data acquisition, so there are so many options and parameters and the advances are there. So in VFD there are one receiver is there where, and here there is a temperature pressure transducer is there or pressure transmitter is there. So uh, depending on the set vacuum, this is the pressure PID controller is there. So depending on the set vacuum and the measured vacuum, this gives signals to PID controller gives signals to the VFD to operate at particular capacity. What happened that initially when this is particularly useful when, because batch reactors, when it will start there is a atmospheric pressure is there, so initially airflow is quite more, so the vacuum pump capacity is defined on how much time how much time the reactor is evacuated, so that will be the maximum airflow. But when vacuum achieves to the desired value, there is a very little airflow, or it will have to, a vacuum pump has to give only vacuum against the any air leakage in system. There is any air leakage is there, only because of that uh, vacuum pump is running. So at that time the capacity required will be very less. So VFD runs on this fundamental. So it what will the VFD will reduce the RPM, and it will eventually reduces the horsepower, and it will control the vacuum. This is the second method. So there are some more advances, and there will be some different options available, and designs. It is designed in a different way depending on the size and capacity. So this is how we control the, how we will reduce the solvent loss with the vacuum controller. We have discussed the different basics like boiling point, vapor pressure, what are the batch distillation, how the secondary condensers is to be used, and what is the how the funda after the vacuum control. So if you have any queries regarding that, I will be available at srsha@udtechnologies.com, or also you can chat with me on udtechnologies.com website. So we can start a question answer session also. Thanking you.
Yes, sir.
Yeah.
Thank you, sir.
Yes.
Sir, a few questions some students have given, like how frequent maintenance is required or needed to be done if it is used for 10 to 12 hour or a day.
Right. So in which maintenance is needed? In which part?
Yeah, for vacuum controller.
So actually, yeah, you're right. See, if depends, maintenance is varying with the valve. Suppose if it is valve control, there are a particular valve is designed for million cycles on off. In VFD, particularly, we have taken care for to design the motor according to VFD. Say if you will go in the electrical part, see there are different motors available are there. So in the VFD control, particularly there are a very maintenance will be very low. Reason behind that we select the motor in such a way that VFD can run means motor can run with the VFD. How VFD will operate. So VFD will see the fundamental of variable frequency drive that RPM is directly proportional to the frequency, right? And
Okay.
so a VFD will decrease the frequency to reduce the RPM from the full mode. So first maintenance will come on the motor. See, there are a certain standards are there in selection of motors. Certain motors are which is not VFD compliant. It will work up to the 50% of rated 100% efficiency. For example, it will run up to 25 hertz. Say in India, the power supply is three phase 440 watt 50 hertz. The frequency is maximum frequency is 50 hertz. So it will run up to around uh, 25 watts for certain temperature. Below that, the motor will get heated and can burn. So, what will take care when we apply the particular vacuum control system in VFD, that will use the VFD compliant motor, which will run very smoothly at very low frequency. So there will be very little maintenance. Say maintenance is that particularly we can say it is a mechanical and instrumentation. So there
Okay.
is no, as there is no wear and tear part, so there will be little maintenance in VFD. But in valve control, as it is a valve on off frequency are there, there are certain life is there in the valves. So after certain that particular life will be after the completion of that valve life, you have to replace the valve.
Okay,
However,
sir.
when we'll go the maintenance on the electrical side, so you have to take care about the instrument. You have to give the complete earthing to the instruments. Other way, you have to check regularly that earthing is given. What are the if there is any problem in the power supply? There will be sometimes voltages are higher. So at certain situations, their instrument can got damaged. But in normal circumstances, there will be little maintenance.
Okay, sir. So there is one another question. So you can stop sharing the slide and we can have a video call. There is one another question like what about the accuracy? How much percent solvent loss is reduced? What is the efficiency?
See that see efficiency depending. See that's why I have told you that see you have to select the particular vacuum. So even you can calculate how much you can recover more. So you have seen my Excel sheet. What I have shown you that
Yes, sir.
you can calculate also. You can also what are the losses and how much you can recover.
Yes, sir. Okay. The another question is that is there any another method beside this vacuum controller?
See that's I have told you again that see you have to use the cooled coolant means see we have uh, in particularly this seminar I have taken cooling water and chilled water. See third you can use also the chilled more chilled than the chilled water like it is minus 20 degree minus 60 degree brine which will cut off the solvent to get maximum condensation, but it is not possible everywhere.
Okay. Okay. Thank you, sir.
Yeah.
Uh, Thank you for sharing the experience on the like solvent loss reduction, and the students are also like they are messaging that they are happy with the session. So once again, thank you on behalf
Thank you.
of Parul Institute of Engineering and
See, and that's
Technology,
why
Diploma
if,
Studies.
right. Yeah.
Okay, sir.
Okay. You can also contact on my email ID. See, there are certain questions. Afterward, it will come. I will also give you answer
Yes, sir.
on
Sure,
that.
sir.
And if there are certain professionals are there which is on in the industries from the Parol Institute, they may also face certain this type of situation in the reality. So they may have some different type of questions also there.
Yes, sir. Of
So they
course, sir.
can contact me on my email ID.
Okay, sir. Sure, sir. Thank you, sir. So you can
Thank you.
like there is one icon phone. You can leave the questions with that.
Yeah, I have to stop representing. No.
Yes, sir. Okay, sir.
Okay.
So there is
Right.
one symbol at the bottom, ring
Mm,
phone symbol.
yeah.
So we
Right.
can click on that.
Okay. Right. Yeah.
Okay.